Okay, so we've done a couple of examples, and here's where we hit a problem. Let's say I've just done an example where we pushed two parameters on the stack. Let's say the address of parameter 2 and the value of parameter 1, both 4 bytes, and then we push the return address on the stack. So our stack pointer is pointing right here. Okay. What if we need to store additional values at the stack while we're executing the function? Well, the thing is, previously in the code, I got to my parameters by accessing or using ESP. So I'd say move into EBX, what is, in this case, 4 bytes away from the stack pointer, and then move into EDX, what is 8 bytes away from the stack pointer. Okay, so I'll have EDX will be a pointer to my second parameter. EBX will be the value of my first parameter. But here's the problem. What if we need to store values on the stack while we're also executing the function? And let's say we want to, let's go back here. Let's see if I can do this a bit at a time. Because what we want to do is, let's say we want to allocate some local variable space. Okay, and in this case, what we would do is say, okay, to allocate local variables, I'm going to say subtract from ESP, 4 bytes. What that's going to do is it's going to subtract 4 from whatever the value is. ESP is a pointer, so instead of pointing here, it'll be pointing 4 bytes in lower memory. Okay, so right here I've got local variable space. So if previously I said move into EBX, what is ESP plus 4, I've got a problem, because what is 4 bytes away from ESP is no longer no longer the first parameter. What is 4 bytes away from ESP now is the return address. So if I do this, all of the offsets from the stack pointer that I used have to be recalculated. And so this would be 8, the next one would be 12, but what if I did this? What if I said 8? Ooh, so now ESP is here, and I've got another local variable. So now I'm not 4 bytes away or 8 bytes away, I am 12 bytes away. Okay? So that's the problem. And is there a solution? Well, of course there is. And the solution is, oh, do you remember back in Chapter 2, when we were discussing all the different components of the architecture of the machine and the organization, and we talked about this one 32-bit register called the base pointer, okay? And we said we'll have more on this later. Today is later. So now we're going to learn about it. The base pointer is a 32-bit pointer. It's used as a fixed reference point on the stack. This is critical. In fact, this, if we can remember it and remember why, is the reason why establishing a stack frame is so important. Okay? So we need a fixed reference point to the stack that is separate from the stack pointer, because we've seen the stack pointer can move. So what is it going to take? Well, before we do anything else, what we want to do after we've called the function is we want to establish our stack frame. How do we do that? Let me show you. We will push EBP, and then what we want to do is make sure the stack pointer and base pointer are both pointing at the same thing. So I want to copy what ESP is pointing at and move it into EBP. So let's go back to that drawing where we had the address of P2, the value of P1, my return address, and here we're going to have the previous EBP because we just pushed it on the stack. So my stack pointer is right here. And then for this second one, I'm going to copy what the stack pointer is pointing at into the base pointer. So right now, I've got both the base pointer and the stack pointer pointing at the same thing. At this point, if I want to do some other things, allocate some local variable space, and say subtract from ESP, let's say 8. So here I want to do this and this. ESP, I'm going to pre-decrement it by 8. Now ESP is actually pointing there. Got some local variables on the stack. EBP is still pointing here. And now when I say I want to move, and let's move it to EAX, I'm going to use the base pointer, not the stack pointer, to access my parameters on the stack. So from the base pointer, I am 8 bytes away from my first parameter, and so on. Okay, so let's get this. I'll be 12 bytes away from the second one. Okay? All right. So I can add local variable space on the stack. That doesn't explain why I need the stack pointer. Well, we kind of alluded to it a second ago. The reason we need it is because we're always, let me go back, sorry. We're always going to be 8 bytes away, okay? So regardless of where the stack pointer goes, EBP always 8 bytes away. The first parameter in the parameter list, okay? So that's handy. That means I don't have to, every time I reuse this assembly language function, I don't have to recalculate the offsets from ESP. All I have to do is establish a stack frame, and then I'm good. Now, the one thing I forgot to tell you, so let me go back real quick and then we'll jump back, is, well, let's just do it here. So we said we're going to push EBP on the stack, and then we're going to make sure that EBP and ESP are pointing at the same thing. So I'm going to move into EBP what ESP is pointing at, okay? So that establishes my stack frame. But what do we do when we want to clean up after we've had our stack? Well, there's a couple of steps, okay? First thing we want to do, we don't know where the stack pointer is gone, so at the end of this, before we hit our return, what we want to do is let's make sure that the stack pointer is pointing at the same thing that the base pointer is pointing at. Okay? Then we're going to pop our base pointer. What does that do? It restores the previous base pointer, or what was pushed on the stack in the beginning. So let me get a different color. Let's draw a stack. So we had P2, P1, return address, previous EBP. And we get down to here. We don't know where the stack pointer has been. We assume we've already used it. We're ready to return to our calling code. So I want to make sure it's pointing at the same thing that the base pointer is pointing at. So what I'm going to do is just copy the contents of the base pointer into the stack pointer. That means I've got stack pointer and base pointer both pointing at the same thing. When I execute this statement, it's going to look at the destination, that's 32 bits, so it's going to copy the 32 bits that the stack pointer is pointing at. Here it's restoring the previous base pointer. I'm going to copy this, move it into EBP. EBP used to be down here somewhere. We don't know where. Somewhere before our function prologue. Okay? So now it's restored, and remember when I do a pop, it post increments my stack pointer. ESP. And that's important because ESP, I haven't even talked about this. Return. Return is an instruction that is also a complex instruction. It is going to pop. Ooh, and let's just make a note of this. This is going to do the same thing as pop EIP. And you say, oh my gosh, you told us we're not allowed to use EIP. And I say, yeah, I know, but I'm kind of changing my mind now. Not a big deal, okay? Because what it's going to do is we're going to pop EIP. So it's going to take our return address, put it into the instruction pointer. Remember, this is how we get back to the calling code. And then it's going to post increment the stack pointer. This is important because in step 5 of the calling conventions we said C++ would clean up what it pushed on the stack. Well, it pushed parameters on the stack. So it's going to clean up its part. We've just got to make sure that we are pointing, stack pointer is pointing at the return address before we issue the return. Okay? All right. I think we've got a little bit more to go, but then hopefully just one more video. See you in a sec.